Hello, everybody, and welcome to our last tech tutorial of the day. The topic is specifying, modeling, and implementing communication flows in multi-agent systems by Bogdan, Okresa, Djuric, and Tomislav Peharda. You can begin your tech tutorial.
Right, thank you very much. Should we go sharing? Tomislav, would you like to share, or will I share the screen?
Sure. Yeah, I can share.
Yeah, cool.
Okay, should be all visible, right? You can see my presentation, full screen. Awesome.
Awesome, thank you. So, welcome everybody to this tech tutorial on specifying, modeling, and implementing communication flows in multi-agent systems. Tomislav and I come from the University of Zagreb Faculty of Organization Informatics and its AI lab. And we're happy to present part of the research that we are doing here during the next 1 hour or 1.5 hours. It will be, well, basically this presentation will show you a part of the research that we have at the AI lab. And it's bound to one of the projects that were funded by the Croatian Science Foundation, the OHI for Games project, which works with orchestrating methods of hybrid AI. Now, I think we can slowly, start. So we have basically in the next 1 hour or 1.5 hours, we'll go through a short introduction about the university, about our faculty, and about the lab, and ourselves included, just so that you know why we should be even talking about this topic, right? Or why it might be worth listening to us. Then we will move to some foundations that we will build on for the practical part, right? So we have to give you some background theory, just a bit of it, in process algebra and how to specify a language, or how it might look like when you specify a language using a specific tool that we used. Then we will move on to what is the platform that we will be describing, and then describing the platform, or basically showcasing what it might look like or what it might work like through a couple of case study examples, or basically through a couple of examples. We hope you will find this interesting, and in the end we will finish with a conclusion. But if there will be any questions, please feel free to ask those in the Q&A or the chat. I think one of those should be open, and we'll definitely have some time for questions in the end. It might be worth noting that, thank you. It might be worth noting that that this part of the research that we did, or most of this that we will be presenting today, is a part of Tomislav's PhD research, which makes this even more interesting and exciting. So let's move to introduction.
Cool, awesome. Yeah, hi everyone. Happy to be here, and thank you for attending this session. So just to tell you a little bit about myself, so I'm Tomislav. As Bogdan said, we are both coming from Faculty of Organization and Informatics in Varaždin. I'm a PhD student for 3.5 years right now, currently doing my thesis in the topic that we'll be discussing more in detail today. And for the past 1.5 to 2 years, I've been extensively in the Gen AI. For the past 5 years, I've been a lot into traditional ML and also deep learning, so convolutional networks and whatnot. And yeah, this is kind of like what kind of like brings me to multi-agent systems and how my entire kind of journey ties together. So yeah, like multi-agent systems is something that's obviously getting a lot of heat in the I guess probably like 6 months. Obviously, multi-agent systems architecture has been present for like several decades now, but with the rise of LLMs and Gen AI in general, this is becoming a pretty popular topic. So yeah, something that kind of like drives my motivation to work on this as well. Aside from my academic career, I'm also yeah, kind of like in industry as well, working with San Francisco and New York City-based startups. Yeah, some of which are pretty cool ones like GM Cruise, Labelbox, Morgan and Morgan, and a few others. So yeah, that's kind of like a little bit about myself. Super happy to answer any other questions, or if anyone's interested to hear some more, let me know. Yeah, we'd be happy to connect. So yeah, I hand it over back to you, Bogdan.
Thank you. So just a short intro on myself. I'm a senior teaching assistant, that's officially called, but basically a postdoc at the University of Zagreb Faculty of Organization Informatics and a member of the AI Lab. And whereas Tomislav is more competent in the professional sense, I'm more tied to the academia and research. And basically, I'm a part of a number of projects that we had at the AI Lab and at the faculty as well. Most of it related to multi-agent systems, gamification and video games, and semantic modeling, and different topics in AI. But these are the core topics and core interests. And I love being well included in projects and cooperating with people in the university and outside of it. And I love international mobility. So I did use some time in different places. I did use some opportunities to spend some time getting better in different places, from University of Graz to Elektrosynchrotron in Trieste to Peharda University, for example, in India. And at the moment, I'm doing a research stay related to multi-agent systems and gamification at the Polytechnic University in Valencia, which is an amazing opportunity as well. So yeah, we are here to just continue working on basically presenting the research that we want to show you today. So yeah, let's move on. Like we both mentioned, we come from University of Zagreb Faculty of Organization Informatics, which is, yeah, you can switch to the next slide, which is basically active for more than 50 years and is one of the constituent parts of the University of Zagreb. The FOI, Faculty of Organization Informatics, actually provides, for those who might not know, provides a very happy combination of informatics or IT, information sciences, organization, and entrepreneurship. We provide study programs in all of these topics, so basically in a very good combination of IT and organization, and happy combination of entrepreneurship and economics of entrepreneurship. Other than that, well, basically in those areas, we provide 12 study programs in all the levels: undergraduate, graduate, and postgraduate, PhDs and specialized programs. And we have quite a number of students on a relatively small number of 150 members of the faculty. FOI is very happy to be a part of however many projects we can manage, and cooperations with the professional organizations and academic institutions all around the world, basically. So yeah, we're always happy to consider some possibilities for cooperation, be it through projects, be it through professional or scientific work. So feel free to contact us in the end regarding, well, some of the topics from here, or if you have some of the ideas that might stem from what we will present to you. Okay, let's move on. So yeah, the AI lab that we are a part of is headed by our, well, both of our mentor actually, Professor Schatten. Yeah, we can move on to the next slide. Professor Schatten, who is ahead of a lot of the projects that we have going on at the moment, or is leading them. I think you can skip, well, basically click on to the next thing, yeah, as well. If we manage to share the presentation, or basically if the presentation gets to you, we have to check that with the support. Then here are the links to some of the scientific and professional projects that we have, and most of our projects are open source and published on GitHub, so they are available to basically anybody who might be interested. And we are always happy to, again, collaborate, and we're open to collaboration opportunities whenever possible. We are working usually in different topics in AI and machine learning, just like the fields of interest that Tomislav mentioned. And then again, multi-agent systems are a topic that goes basically through most of the research and projects that we work on. We love playing with games on basically all levels, and especially applying game-based mechanics, game-specific mechanics to non-game contexts, which is basically applying gamification, then computational intelligence, web mining, semantic web, and so on and so on. Let's move on. Yeah. So in order to allow all of us to actually follow what Tomislav will be presenting, and to understand how, what, and why the platform and the language that we will be presenting makes sense, it would be very helpful if you are, or basically if we present some topics that are fundamental to the whole research. One of those topics is process algebra. So process algebra basically gives us a way to describe processes as agents, and that is what we are working on. We are working on abstracting processes in general, like whichever process, as an agent, right? Because it can be described as an agent. Okay, so if you move to the next slide, then we can see that process algebra is, or can be described as, a collection of related approaches for formally modeling concurrent systems. Now, the keywords here are formally modeling, right? Or basically formally and then modeling, because creating a model in itself is basically abstracting something from the real world, but keeping and representing it in a different context, but still keeping the key components which make it that very specific, right? So basically, if we create a model of a smart home, for example, we will not be taking all of the data and all of the information available, but we will take whatever is needed for our approach, or for the goal of creating that model, right? So we need the data, or we need some features of different objects of the model, but well, different objects of the real world situation that we are modeling. But we don't need all of those things, or basically all of the features, because that would be too much. When we need as many of those as are needed to successfully model the situation, the real life scenario, right? So that's about modeling. Now, formally modeling means that the model can be described in a formal way, which is akin to mathematics, for example, right? To mathematical logics and similar formally defined systems. Now, what modeling a situation in a formal way allows us is to define a set of rules that can be applied to the initial model, and using those rules, or applying those rules to the model, we can change the state of the model. We can change the relationship of the concepts, or basically of the objects, or of the elements of the model, and so on and so on. So having a thing formally described makes it easier to work with it, and also makes it easier to understand it in a way that is not necessarily linked to the language that we speak, to the natural human language, right? Apart from that, or basically on top of that, we have the ability to have a formally modeled system that we can first use as an input to a simulation, but then again, we can use it to validate a simulation, validate a modeled system, and show and see basically how very applicable, how very successful the model was based on the real life scenario. And then we have concurrent systems, right? Which is the third keyword here. So we have formally modeling concurrent systems. Well, concurrent systems would have different processes that can be running in the same time, right? Or basically as concurrent processes, right? So they can run in parallel. Now, they can run in parallel, but not necessarily. We can have a sequence of those as well. So that's about formally modeling concurrent systems. So we use process algebra to basically describe different processes. And what we have here is that process algebra allows us, or basically provides, a framework for describing complex processes and their interactions using algebraic equations. Which means that there's different formalized systems that allow us to work with a formal description of a complex process, right? Which consists of individual processes, which may consist of different actions, for example, and apply some equations to that model and see how the model then behaves, right? So we can see that the model goes from one state to another and to another and to another through different equations that we apply to it. And different equations basically mean transitions from one state to another. Now, the key concepts that we have in process algebra are these three. So basically, we have processes, we have actions, and we have operations. Now, processes are basically whatever process you can think of, right? So it can be the process of, giving a talk, which we are doing at the moment, right? Or listening to it. Then the actions would be different elemental, or basically sub-level concepts to a process, right? So the actions in giving a talk or attending a talk would be, I have to register, I guess. I have to open the conference. I have to attend, maybe ask questions, which is optional, and so on and so on. Now, the third key concept here is operators, right? And these three are only a subset of all the available operators. And those, in a way, govern or formally showcase or define the different relationships between processes and actions, right? So we have sequence. For example, the operator of sequence tells us that we can have processes which are set up in a sequence, right? One after the other. So if we look at attending a talk as a process and registering for a conference as a process, then we can say that first you have to register, then you have attend a talk. You can attend the talk of that conference, right? So that will be a sequence. Then there's a choice, which means that we can have two things happening basically based on a specific input, right? And then we have processes running in parallel, which means that both of those will be conducted at the same time, right? Now we can use those operators in combination, so there's no one single operator that's the only one that we can use. We can use a combination of those to basically model a complex process or a system of processes. On the next slide, we have an example of a system that can be defined, or basically a process term, which is defined as this: first A stop, then B stop. The symbol in between is a parallel. So basically, we can have the first element running in parallel with the second one. And then plus sign basically means that at this point in time, another process can happen, and that's the third one. This example is taken directly from the book reference below, but let's just say that if we start with 3 processes waiting for something to happen, then if the signal C happens, right, which is the can I show this somehow? No. Is there a no, doesn't matter. Anyway, so what we have here is if there's sorry about this. What we have here is that if the C signal happens, then we directly move to stop. So you can see the horizontal arrow right there, right? From the starting point, C moves to the right. Yeah, exactly. And we basically move towards the state where C is stopped, but it can still synchronize with the other processes, A and B. Right? Then from the starting point, we might have A or B happen in parallel. So if A happens, then we move to a spot, to the state of the system where a process is stopped, but it can still synchronize with A or C. Well, basically with C, right? Which is which we can see in the curly brackets. After that, B signal is delivered to the process B, and it will be stopped as well, or it can still synchronize with process C. So basically, what we see here is something that we can think of as, for example, two different processes, or basically two different devices on a network. For example, this could be three devices. Let's say A would be a smart light. Device B, so the B stop thing, would be a smart thermostat. And a C device, the C dot stop, right, would be a central controller. So we have the possibility that the smart light will basically stop operating, right? Or basically turn itself off or on, doesn't matter. Will do something, which is action A, and it will stop, but it can still be synchronized with the central controller. On the other side, we have B dot stop, which would mean that the B receives a specific signal, for example, adjusts the temperature and moves to a spot on the right, which you can see with the arrow going from P along the B arrow, right? Or the smart controller can basically just do something and synchronize both of the devices. Now this is a very should be simple example, but it works with processes and the signals. Now on the other slide, we are moving towards process algebra, right? Because we said at the beginning, we're moving to process calculus, excuse me. Because we said at the beginning that we love formalized system because we can use different formulas or different functions on it, right? To model or to change the system, to interact with it. One of the ways of doing that is pi calculus, right? It's one of the process calculus implementations. And we were interested in modeling processes as agents. Now, the pi calculus gives us a lot of stuff that can happen. But if you click once more on the slide, then we get this example, which is from our teaching materials that we present to students. And basically the CRV at the bottom, right, the third thing would be an agent, which is a worm, a computer worm, right? So what we see here is three distinct agents, which is A, B, and C, and the fourth one being the worm, the last row one, right? Other than that, we have three communication channels, because you see that we can describe systems which are distributed using the concepts of processes and communication channels. Now, communication channels in this example are K1, K2, and K3. Now, in the first three examples, we have agents which have names A, B, and C, and they are connected to channels K1, K2, and K3, receiving some data, and then taking form of their data, or basically of that piece of data, or basically taking a role, specific role, and then acting as themselves, right? On the other hand, we have the worm agent, which has K1, K2, and K3 channels, and it's sending data to those channels, right, in parallel. So basically at the same time to all of them, which means that it sends itself its own definition, right, to the three agents who have no idea what's coming their way and don't know about cybersecurity. And basically they turn into a worm, which immediately sends its definition to other agents, right? And those agents then take the definition, get infected, and distribute further along the networks. So basically, in this way, we can, in this rather simple example, we can, on a very abstract level, describe the idea of a computer worm. Now, let's Tomislav will take over and talk more about this thing, but just a bit more. Let's describe how to specify a language. Yes, thank you. Yeah, and the next one as well. So how to specify? Yeah, you can open the whole thing. So how we can specify a language? Well, it's not extra complicated depending on how very detailed you want to go, right? So what you can see on the left side is a language specification for simple arithmetics, right? For adding, subtracting, multiplying, and dividing numbers. So what we can see here is if we have an expression, that expression can be within parentheses, or that expression can be one expression and then division symbol and then another expression and so on until we have only a number, right? Basically saying that an expression is a number. Well, a number is, you can see that on the left side on the third line from the bottom. A number is basically a set of digits, and a digit is a fragment that can be from 0 to 9, right? Exactly. Then again, addition, subtraction, multiplication, and division are symbolized by these symbols that we have here. So addition is a plus symbol, subtraction is a minus symbol, and so on and so on. Thank you, Tomislav. So applying these rules to the example on the right, we have an expression which is, to us, it's obviously a arithmetic expression, right? So it works something with numbers, doesn't matter. Now, applying the rules on the left, we cannot say that we have a number because we don't know about that, right? Because we have an expression in between. Well, we have an expression with subtraction inside it, right? Which is the first row. But then we have two expressions, one on the left, one on the right, and we have expression within the parentheses. That's why we remove the parentheses and we take a look at the expression within those, right? Then we have an expression with a division symbol, which is /4, right? Divided by 4. So then we have two expressions, which is the left-hand side, and 4, which is only a number, so we can't work on it anymore. Then we have an expression that's, that's basically with the multiplication symbol, right? And those should have been two different expressions, and so on and so on. So basically, we apply the rules, we apply the grammar all the way till we get to all expressions which are simply numbers, and we know what's happening with all of that. So that was the introduction. That was the theoretical introduction to process algebra and how to specify a language. And now Tomislav will do the interesting part.
Yeah, 1 sec. Let me just refresh because it seems that some of the slides are not appearing here for whatever reason. Okay, let's take a look. Okay, yeah, there we go. Okay, cool. Yeah, so, well, there's just a little bit more, well, not so much theory, it's also about practice, actually, but just want to give you a little bit of introduction to what multi-agent system is. Main reason being that's obviously something that we're going to speak a lot during the rest of this session. So, yeah, like Bogdan gave you a good overview on kind of like how do you model and I guess design relationship between different processes, kind of like what are the old execution flows. Sometimes it can be sequential, sometimes it can be parallel and whatnot. So this is kind of like a good base to speak about an agent more from a practical standpoint. So what is the definition of an agent? Agent can be described as an autonomous unit, as an autonomous piece of software that is capable of processing a task or processing, essentially conducting some business logic on its own. So that being said, it does not, the main idea is that it does not have too many or any dependencies on other systems. So it's kind of like, you have a piece of software which is responsible for receiving a weather, for example, or like computing some mathematical formula. So it's kind of like very isolated type of task, which that single agent is capable of achieving on its own. And yeah, kind of like what triggers the business logic of an agent is either an incoming request. So for example, you as a user might want to request this, like you have a formula, you have some values that you want to apply into a formula, you send that value, send that formula to an agent as an kind of like incentive, and or a prompt, better to say, and the agent will be doing some calculation based on your request. So that's kind of like one way to trigger an agent. And then a second way is on a timely schedule, which can be maybe even better described as a cron job. So imagine that you have your agent who is consistently like gathering and collecting data throughout the day. Maybe there's some like database that it has access to, and at the very end of the day, the agent wants to examine that data and maybe do some action on top of that or some operation. So that being said, on a timely schedule means that the agent will trigger itself once a day or whenever we set it to trigger. So those are kind of like two basic approaches to how to think about how the agent logic gets executed. And now to give you like how do we define a multi-agent system? Well, it's pretty simple. It's a multi-agent system is a cluster of agents. And the thing is that when you have a bigger goal, which is like a more complex task, for example, now with Gen AI, we might be, I don't know, you guys probably saw GPT-4o demo, and it actually has lots of features. Like first of all, you have a model which is transcribing your voice, your audio. So that's like one agent that could be described as one model. Then you have something that's like LLM model potentially, which is using that transcribed text to generate an output, a textual output. So that could be described as a second agent. And then the third agent could be simply a model or agent which is producing a response in an audio so that it gets back to you. So now if you had a single agent doing all those three tasks at the same time, obviously it is possible, but then you kind of like start creating a tech debt, and at the same time there might be constraints which you could potentially run into. So speaking of those large language models, obviously they're super large, and when you have like 3 models which are pretty large, having all of those in the same infrastructure, in the same, let's say, server machine or whatever, makes it pretty difficult to run. And at the same time, if one model for whatever reason fails, likely all other 3 models, if they were hosted in the same machine, would kind of like fail as well, because there's no good error handling, so to say. So that's the reason why I want to actually have multiple smaller agents, which are much easier to handle, much easier to set up and extend and modify and whatnot, instead of having one big agent. So they work together, they exchange messages, messages of kind of like their processing, so that they can, when they work together, they can achieve that bigger goal that they have. So, if you're speaking of GPT-4o, the goal was to get the audio message, like you take an input audio, and the goal is to create an output audio. So, those three agents could work together to achieve that goal, which one agent might not be capable of doing on its own. So just to kind of like recap, so an agent is like a small piece of software which is like specialized in some particular task. And then when we speak about multi-agent systems, it's like cooperation of multiple agents which are communicating together. Each of them has a specialized task, or maybe there's multiple of the same instance. And the idea is that they work together to achieve a bigger common goal. So that being said, as we said, yeah, like what we want to present to you today is our platform that we built as part of our AI lab, and which is also part of my doctoral thesis. So we created so this is still, it's pretty much done. There's still some polish, obviously, like we still need to update the documentation, and some other stuff will kind of come as part of my thesis. But the thing which we developed is like an open source platform, which enables you to better orchestrate and coordinate your agents, or we can also call them microservices within multi-agent system architecture. So that being said, when you have lots of those agents that are communicating together to achieve a bigger goal, it's very crucial to properly design those relationships. So you can imagine if you have like hundreds of agents which need to work together, specifying all those communication kind of like directions between two agents or multiple is pretty difficult. So our platform is here to make that easier, make that job easier, and at the same time offer plenty of other functionalities, but also make your, let's say, your code and your application more safe, just because you're able to like consistently at all times see what are the relationships between all the agents and whatnot. Obviously, I'll get to that in a second. So what is that orchestration refers to? So first of all, it's about specifying communication flows, which means if you have 10 agents, those 10 agents are communicating together. What pairs of agents are communicating, and in what sense? What is the protocol they communicate over? What is the format of a message? And so on and so on. And the second thing being the dependencies between those agents. So like those agents might not all start at the same time. For example, maybe agent C will only start once agent B completed their task. So there are definitely some dependencies which are kind of like needed to make sure that all that orchestration is covered from all of the edges. So what is the focus of our platform, or kind of like what are the well, yeah, I guess the focus is a good way to describe it. So it's first of all to support communication flow specification, interaction between the agents, and kind of like the execution flow. And the second thing is that if you have your agents already built, the idea is that you can reuse them very easily. So if you actually want to bring this platform into your application, you would definitely need to do some coding, that's for sure. But your agents that you already have in place should only be updated by like a small amount, if any. And that mainly touches on the communication flow specification. So, like very modular and kind of like easy to extend. That's the idea. So I have a link to our GitHub repository here, which you can obviously visit and fork the repo and try it out yourself. At the end of this present session, we will also have not at the end, shortly, I will also show you how this actually runs. So kind of like to touch a little bit and speak about what is the problem domain. So in the traditional multi-agent system frameworks, and especially the ones that support distributed agents, each agent individually implements communication flow. So as I said, agents are they're autonomous units, meaning that they do not really, like obviously you can make it, but the idea is that they do not share the logic with other agents. So I might have a piece of my software, which is my agent, and you might have your own. So obviously there will be like you coded it one way and I coded it my way. They're not sharing the code. And each of them, since they need to communicate, both of them do require to have some communication mechanisms in place, be that the listener, be that some logic to send a response and whatnot. And with those frameworks that are currently available on the market, as I said, mainly the distributed ones, each agent needs to implement that logic individually, which makes it, pretty prone to failures. So imagine that, I guess some of the consequences are listed down there, but we can go over them. So like, if you have like multiple agents implementing the communication flows individually, this leads to code redundancy as a one thing, but also more room for failure. Because maybe if you go and update an agent A and you forgot to update agent B, obviously that means that you have more room for failure. There's also, from that point, also we get to the inconsistency of communication flows. So maybe agent A was designed to communicate with agent B, but not vice versa. So, like you do not have a good visibility into what are the pairs of agents that communicate. There's also the problem of weak extensibility. So if you need to add a new agent to the multi-agent system, this requires changing existing agents, which is pretty problematic, because you constantly need to be updating your communication flows and keep track of everything. And lastly, kind of like the last consequence is that you do not have a single source of truth that would describe all the communication flows in a multi-agent system. So as I said, agents are autonomous units. Each of them implements mechanisms for themselves. So how do you have a holistic view of what is the communication flows between all those agents? You essentially need to look into the business logic of each individual agent, and there's no way for you to like have a good holistic view, which is kind of like ground truth. And all that actually leads to difficult orchestration. So it's leading to problems when it comes to coordinating agents, when they start, when they should shut down, and how they communicate and whatnot. And the solution that we have for this problem is the platform, which is kind of comprised of two components. The first component is a programming language for specifying a communication flows. So it's based on P calculus that Bogdan has previously described. And the idea is that you have a specification file with .api extension. And in that file, following our programming language, you specify what are the pairs of agents that communicate each other. And obviously, it's not only about the kind of like defining the relationship, but it's also about what is the format that they communicate in, what is the protocol, and whatnot. So one thing being programming language to specify those communication flows, and the second thing being the declarative engine that processes the specification and establishes connection between your agents. So you can imagine that there's a central unit, our platform, which takes that specification that you write and then connects your agents together so that they can communicate. And that means essentially passing the messages between them and letting them know if like one needs to start up and the other one needs to shut down and whatnot. So it's really about orchestrating those agents so that they are properly coordinated. So what are the key elements of our platform, and better, I guess we can just say our artifact. So the five elements, which are kind of like the entities that we have, are Holland, environment, channel, agent wrapper, and agent. And those are kind of like from up to bottom, where the Holland actually is the highest in hierarchy and has the most power across them. So this will make more sense just in a second. So what is a Holland? The idea is when you have that multi-agent system, that you have an agent which is delegating a work to others. So Holland is type of agent, which is actually responsible for making sure that like you have that if you have like multiple multi-agent systems, that your one multi-agent systems could be described by a Holland, which is the representative of that multi-agent system, of that cluster. So it's kind of like you can imagine, I guess, as a president of all agents within the same cluster. And the Holland is then responsible for delegating the work and whatnot. Obviously, this is not a necessary concept. It's a concept that you may use if you have multiple multi-agent systems communicating together, but it's not, it's very optional. The way how, so if you do have a Holland, or better to say, if you have multiple Hollands, if you have multiple multi-agent systems that are communicating, those multi-agent systems would be communicating over environment. So the idea is that if you have two clusters that need to communicate together, they have input and output channels or environments. And the idea is that if your cluster produces a message that needs to reach the next cluster, it would do so by sending that message to a environment interface of a Holland. So the idea is that environment serves as a interface to inner agents, but you never know what are those inner agents. You just have the concept of like a cluster of all those interconnected agents. So Holland and environment, those are kind of the concepts when it comes to communication between multiple clusters. And then channel, agent wrapper, and agent, those are kind of agents, type of agents within the cluster itself. And perhaps I can explain those from bottom to top. So an agent element as an agent actually refers to that piece of software, the autonomous piece of software, which you built. It doesn't matter what language it is built in. It can be any business business logic you like. It could be even a HTTP server if you like, actually. And it's that modular piece of code that will not really change much or at all. And then we have agent wrapper, which is responsible to pass any messages to agent that are coming from other agents. So it's kind of like a proxy to your agent, which implements the communication flows for you. So let's say that your agent was defined to communicate over TCP, and you have another agent which was designed to communicate via UDP. So agent wrapper would be kind of like responsible for that, for bridging the gap between multiple communication flows. Multiple communication protocols. So it's kind of like making sure that your agent business logic remains as is, and the wrapper is used as some sort of adapter. We could actually say that way. And then the last element here is a channel. So when your agents need to communicate, they do not communicate directly, but it's more so that they communicate over a channel. And what this helps with is that if you have multiple agents that are interested in the same message, so you have like agents A, B, C, agent A produces a message, but both B and C agents are interested in that message. Agent A sends a message to channel, and those agents B and C that are interested in that message will be subscribed to a channel and read from that channel. So that's kind of like a overview on the key elements of the artifact. And here's I guess a visual representation of what I have just described. So as I said, we have I guess we can go bottom up. So we have an agent which is wrapped by an agent wrapper, which is that adapter logic which I mentioned. We have a channel. So this agent on the left is producing a message, sending it to a channel, and then agent B is subscribed to that channel, and through the channel receive that message. And what I also added here was this concept of Holland. So you can see that a Holland is kind of like a cluster. We see that all those the agents are inside the Holland, inside a cluster. And on the edges of the Holland, we have environment on the input side, which is on the left side, and on the output side, which is on the right side. And now if we had multiple Hollands, those environments are kind of like the way how Hollands would communicate. columns do not communicate directly with the inner agents. They communicate over environment. What are the types of communication that we allow? So there are different types of communications depending on the level of the agent. So I guess we can maybe just quickly jump onto this figure over here. So on the foremost right, we have an agent. In the middle, we have agent wrapper. So those two instances communicate over Netcat. They can communicate over Netcat, WebSockets, HTTP, file, stdin, and so on. However, agent wrapper, which is responsible for proxying those messages to an agent, communicates with channel only over TCP and UDP. So yeah, that way, if your agent was designed to use, like multiple different communication protocols, or actually it has on a disposal to utilize those multiple communication protocols, it's totally good to do so. However, to simplify the process of this message passing mechanism, the agent wrapper communicates with the channels only via TCP and UDP. And what are the supported formats? So first of all, you can just sit in the row format. So obviously in the row format, this means that there's no transformation being applied. So your message, as you send it in, that's the same format in which it will be passed to the destination. But we also support for XML and JSON. And those are like the main features of those two are that if you do use those formats and kind of like specify that your message will be in those formats, we can use it for better, like maybe you want to apply some filter logic, or maybe you want to apply, you just want to extract some kind of like metadata from the message, which will be used by channels. So in that case, specifying JSON or XML as a format is a super useful. It's kind of like a metadata to our orchestration platform so that it knows what needs to be done if there's some special case. And as I said previously, so the agents do not only specify like communication, obviously they do communicate, but they might also start or exit in different times. So for example, we might have two agents that are communicating together. Agent B will only start when agent A has completed. So what we call those as execution flows. So the execution flows that we support right now are sequential, meaning that agent A goes first. Once the agent A is complete, we go with agent B. Or better to say, agent B starts at that time. We have parallel, which means that both A and B would start at the same time. We have recursive, where once the agent A is completed, if it's like, let's say that we have one-off agent, one-off business logic. So whenever the business logic completes, the agent shuts down for whatever reason. And then with the recursive execution flow, we will keep starting it up. We also have a failure safe execution flow. So for example, if you have you have agent A, which might fail. If agent A fails, you want to start agent B. So it's kind of like failure safe. And we also have a success type of execution flow. So start agent B only when agent A succeeds. And those are kind of like the 5 execution flows that are currently supported. And obviously, if there will be need, we'll be also looking into maybe covering some of the more special use cases. So right now, I spoke mainly about the communication flows and also execution flows. But those two kind of like key features also come with a lot of supporting features, some of which are that we support arguments. So I'll be showing a code in a second, but the idea is that if you want to make your code very dynamic, maybe you want to pass in some arguments to your agents, you're totally free to do so. You are able to bootstrap an agent by just providing it as a function. You can imagine that you have a function which you call, which will bootstrap an agent based on those arguments or parameters that you send in. As I mentioned previously, we can also, if you use JSON or XML formats, we can apply some additional transformation or filter logic on top of it, which is done on the channel. And you can start agents as Kubernetes, Docker, or Unix processes. So you have your own agent, which might be hosted somewhere, or might be also a process that you just want to start. You can start it as a Kubernetes process, Docker, or a Unix process. And I'm going to show a little bit of code right now. So what we have following is we have a few steps how you actually go about utilizing our platform, and then we also speak about the case study examples, just to see how a particular real case would be transformed into our kind of specification written in our programming language. So okay, so here we are in my VS Code. So I'm just showing you those examples of the specifications that you would write to specify how those agents are communicating. And what we have here, so this is I'm showing you the most basic examples. So we have we have a channel C, and then we have a couple of agents. We have blast std in, std out, and we also have blah file std out. So what is this specification set is that for agent blah std in, std out, we will take an input from channel C. So we will be waiting for a message to come from channel C, in which case we will start processing that message. Contrary to that, with the second agent blah file std out, we actually have that agent is the one who will produce the first message and send it to agent C, to channel C. So the idea is that blah file std out would start and it would produce a message. That message would be sent to channel C. Channel C would proxy that message to all the subscribed agents, and in that case, blah std and std out will be receiving that message and processing and kind of executing a business logic. And here at the bottom, we are actually specifying that both of those agents are started concurrently. So that's one of the examples. I can also show a few more, although we'll go over them in a bit. So that's a too complex one. I guess this is a very similar example where instead of channel C being just a proxy, it also utilizes the transformation and the transformation process. So what it does here is that if we have message, whenever a message arrives to channel C, which is in the JSON format that is specified over here, the channel C will transform that message into XML. So that way, your agents, we can imagine that blah std in, std out was really not designed to communicate over JSON. So we can utilize channel business logic to transform that message from one format to another format. So those are kind of couple examples that we have here. So yeah, we'll cover more of those in case studies. So let me get back to the presentation. Okay, so I'm gonna go quickly over some of these steps, how you would go about utilizing the platform. So the first thing is that you actually need to kind of design a communications architecture. So that means you have lots of your agents which you want to connect together. So the first thing is you need to specify, at least conceptually, what are the pairs of agents that communicate together? Is it A with B? Is it C with D? Is it A with D and whatnot? So you kind of if you took a paper, you just draw it and draw on a paper what are all of your instances of agents that are communicating together. The second thing you also want to think about is what is the format of messages that those agents would share. So one agent might be implemented to communicate via JSON, the other via XML format. So you want to keep account of that so that you can accordingly do any transformations as needed. And then the another thing, kind of like point to think about is what are the interdependencies between agents? Does the agent A maybe start before agent B, or do they start at the same time? So what is kind of like the flow, execution flow that you wanna choose? So once you have that conceptual idea of your communication architecture, you actually wanna convert that into our specification. So as I've just shown you, so now that you have conceptual idea, you actually wanna program it within our programming language. So what you would do is you would create a file, you would have extension.api, and you wanna convert, like you wanna use our programming language with all the syntax elements and whatnot, and kind of like convert your conceptual architecture into our programming language, into a specification. So that's the second step. And then the third step is you want to define contract between your kind of like what is the contract for input and output of your agent. So as I said previously, the idea is that you do not change your agents a lot or at all. So that being said, as you have that wrapper agent over your agent, which is there to bridge any communication gaps, you need to specify what is the how does your agent actually communicate? Is it via HTTP? Does it go over TCP, UDP? What is the communication flow? And just to quickly show you what it looks like. So if I switch to, where is it? Okay, so here's one of the agents that we have. So we have blah std in, std out. So we give it a name. So we say that name is the blah std in, std out. We give it some description, and then we specify what is the type of this agent. How do we want to start that agent? How do we want to start, or better to say, how do we want to interact with that agent? Is it as a Unix process? Is it as a Docker instance, Kubernetes pod, or what else? And then you specify what is the input and what is the output. So what is the, essentially interface contract that is needed for you to communicate with, for the other agent, or better to say, with our platform to communicate with your agent. How does it reach your agent? So is it via std-in? Is maybe there a HTTP server that the platform needs to access, and what else? So that's the second step. That's the third step, and then the fourth step is implement agent business logic. So as I said, we support, like, we are very much into the idea that you don't have to change your agents much. So you are totally free to use your agents if you already have them existing. Otherwise, if you do not have them existing, obviously you need to develop them separately from the platform. So, like if you kind of like look from high level, you need to first, when it comes to practical steps, you need to define communications flows as part of API specification. You need to create IO input-output contract for each of your individual agents. And then the third thing being kind of like optional. If your agents do not have business logic, you want to obviously code them. Otherwise, you are pretty much done. So I have a demo here how to run locally, but honestly, that's not really it's just going to show you the messages in the terminal, which is not really the point of this. It's more for a tutorial if you actually need to if you want to run it so that you can see how things would go. So if those slides will be shared with you, obviously you can use this video to just see what is kind of like the expected messages that you see in a terminal. Okay, so just because we have 20 more minutes left, I will skip the text slide, and I guess we switch on to the case study examples. So yeah, I guess we have three more examples here. Bogdan will be kind of like describing them, and then I would show you visually and through a code how those would be implemented. So I think we'll be probably done in about 10 minutes.
Okay.
Bogdan, do you, yep.
Yeah, that's cool. Okay, Tomislav, thank you. That was really nice. So yeah, basically, what I don't know what's happening with the camera. It doesn't matter. Anyway, what we want to show now is how this thing that Tomislav described might actually be used in a specific scenarios, right? So we have 3 case studies ready with 3 examples, where the first one is a traffic management system. Now, since the emphasis of this part of the presentation is not on describing the example itself, but giving you the example on how the solution that Tomislav described can be applied to that example. The description of the example of the case study of all 3 of those, the description is AI generated, or basically generated by ChatGPT, just because it was easier to create a story which will then be translated into communication flow of agents, right? So if we move on to the story, then think of the first example as being the traffic management system, right? So we are in a bustling city that has traffic lights, it has cars, smart cars, and smart traffic lights. We have intelligent vehicles and of different kinds, right? And then these agents, of course, collaborate in order to manage the traffic flow in the city, because we want it to run smoothly and to have no congestions. Now, different traffic lights which govern the traffic flow can communicate with each other and can communicate with vehicles as well. And vice versa, vehicles can communicate with them. We have some sensors as well, and the whole system works very well together in a way that makes the traffic flow with no problems, or basically with at least problems as possible, right? And that makes the whole system not necessarily problem free, but definitely flowing freely and allowing commuters to reach their destinations efficiently. Now, if we move on just one click, then we have we have different agents which we can identify in this description, which are traffic lights and vehicles. And then we have different communication flows in this particular example, which would be different traffic lights can communicate with each other. We have vehicles to traffic lights communication, right? Because vehicles can send some data to the traffic lights. And then, of course, we have vehicle-to-vehicle communication as well, which makes the whole flow rather easier. Now, we move on to modeling the system.
Yeah, so here we can see visually. So the idea is that after theoretical background, each of those cases we cover with the visual representation of how the system would look like within our platform, but also we provide a code for specifying those communication flows. So the idea is, we have the blue boxes are channels, which we said are used for proxying the messages between agents, because they do not know of each other. They're just like commuting through a channel. So on the left side, we have a traffic light, which decides, as Bogdan said, it has a mechanism, business logic to for example, say it's a green light, it's a red light, and whatnot. It sends that message to a channel named traffic. And then we have agents, multiple agents, vehicle agents, which could be, like instances of the same agent, just like, well, I guess an instance of an agent is just sufficient to say. And those agents are subscribed to channel traffic. So whenever traffic light sends something to that channel, they will receive that message, and then they can do some action. So if you have a vehicle which needs to move forward, like it based on that prompt, based on that incentive, it will know when is the time to start moving, right? And agents, those vehicle agents might as well produce a message. So for example, they want to inform other other attendants in the traffic, so other vehicles, that they're in what direction they're going. So what they would do is they would send a message about their direction to the channel vehicles. And considering that all vehicles are connected to that channel, they will be receiving messages about where each vehicle agent is moving into. So that's the visual representation. And then this is kind of like how you would go about specifying within our programming language. So you have two channels, traffic, vehicles. You have traffic light as a channel, as an agent, which produces a message itself and sends it to traffic channel. And then we have one or multiple vehicles, which they send a message to vehicles channel, depending if they have something to send, but at the same time, they are receiving a message from that channel as well. So that's all for case A. I guess we can also then switch to case B.
Yeah. So in the second case that we prepared for you, or basically the second example that we prepared is about supply chain management. So just to cover a couple of interesting scenarios, right? Interesting different scenarios from different points of life. So if we move on to the description, again, helped by a large language model. If we move on to the description, then we have yeah. You can switch the slide so everybody can read it. Yeah. So yeah, this thing. So we have a city, right, and the supply chain that operates very well all together. Now the point is that we have different entities in the supply chain. For example, suppliers, manufacturers, warehouses, retailers, and so on. Or basically these four in our example. And we can try and actually not only implement these entities on their own, but implement them as agents, or maybe think of agents that Tomislav will describe now as maybe decision support systems or similar systems that can be abstracted as artificial agents. We can recognize a couple different agents in this particular example, which are visible on the next slide. And we have communication, which works with, yeah, you can click, I think twice more. Yeah. Okay, cool. Yeah, another one. So we can work with suppliers to manufacturers, manufacturer to warehouse, and warehouse to retailers, of course, because that's just different types, different entities in the whole process. But we have one more communication flow. If you just click once more, then we have all-to-all, which is very interesting as well, because we basically can have either the environment or something similar that's not necessarily crucial, but a very, very good point to model as well. So Tomislav.
So again, here we can see it visually. So it's pretty sequential right now. There's no so much about going all around. So what we have here on the left side, we can have multiple supplier agents, which will send a message to products channel whenever there's let's say some product available. Agent warehouse is listening to that product to that product channel. Obviously, that agent can be responsible for high variety of stuff. One of these could be, hey, go pick up those products and put them into a warehouse, so to say. Once that is done, agent warehouse sends a message to channel storage, and the channel storage is now all the subscribers to this channel are now being notified that the storage is back full. And so if we have, in this case, we have retailers subscribe to that channel, so they will be able to, let's say in their web store, they can say, okay, those products are now available. We are able to ship them to our customers immediately, so they can update their stock, so to say. So yeah, that's kind of like visual representation. How this would look like from the code representation is, so a couple of channels, products and storage. We have suppliers, one or multiple. They're sending a notification to product channel. As we said before, a warehouse agent is subscribed to product channel, waiting for information from suppliers. Once that arrives, it does some business logic and sends a message to storage channel. And then we have retailer 1, retailer N, which are subscribed to storage channel and then are able to consume that information. And yeah, we can now also hop to our last use case, which is KC.
Yeah, so the last use case that we prepared is, well, it's located in a hospital emergency department. But the point, if you switch to the description of the case, then we can see that it basically works with patients, nurses, doctors, medical staff, administrative staff, right? The point of this one was that the channels that we can define and that we model as well can take on different kinds of transportation, basically technologies, right? And different kinds of security and so on and so on. Because, for example, because in this example, we need to take care of security of data and privacy of and basically keeping the privacy of the data that is being transmitted, right? So we use channels in a bit different way, or basically we need to take more consideration of how we implement the channels. So yeah, we have all those people in the medical system, and we're trying to create a well-orchestrated system. Again, we can talk about agents not directly as patients or doctors or nurses, but as different types of decision support systems, or basically systems that can help bring a good decision, or that can help ease the way of doing specific tasks. Yeah, we have agents and communication flows that you can, I guess, based on patterns, you can recognize now. Different communication flows between different actors in this particular scenario.
And again, here we have a visual representation. It's actually very similar to case B. And so this is very basic example, or we have concepts which would be able to support this use case even better. So Holland's specifically. However, just to keep it for now, for this session, to maybe keep it more lighter, because there's a lot of content that we went over. I didn't want to complicate too much, but I just wanted to emphasize that there's a way to make this even nicer with Holland. So yeah, just as a heads up. So on the left side, we have like multiple patients, multiple instances of a patient agent. They might come to a hospital. They have a problem. So what this means that they would send a message to channel injury. Subscribers to that channel would be nurses. So whenever they receive a message, they go kind of like the agent nurse goes to analyze that message, see what's the information there. What they do is kind of like triage the situation, do the investigation, and generate some results on kind of like what are the next steps. So the triage results are then sent to channel triage results, to which doctor agent instances are being subscribed. So obviously, when they receive those results, they can react to them. So obviously you would not want that all of them react to them, but only one of them. So that's where the idea of having a Holland would be helpful, because you have, like, you could implement those doctors as a single Holland, where you have doctors as like inner agents, but you also have one agent which is delegated to specify to what doctor agent you actually want to publish message to. So that way you don't have to publish to all of the doctors, but you only send to a single one, which is, let's say at this moment, free to take a look. Doctors would then produce an output, which is kind of like a therapy, send it to channel therapy, and then administrative staff is subscribe to that channel, receive that therapy, and obviously do some follow-up logic. So looking from the code base, yeah, we actually have 1 more minute, so I'm not going to go deep into this. But yeah, here's a basic example how you would specify communication in our language. So yeah, that's all we had for today. So just to shortly conclude, so what our artifact is comprised of, it's 2 things. It's a programming language, which allows you to specify execution flows between agents, but also how those agents communicate and interact together. So so that's like one part of the artifact. The second part of the artifact is a declarative engine, an engine or a platform which is actually consuming those specifications and is responsible for orchestrating, coordinating agents, but also any message passing events. So this platform is designed to actually support existing use cases, not only the new ones. So that being said, if you already have agents in your application, all you need to do is kind of like follow the steps which I described previously. Define the communication flows in the programming language, implement the I/O input-output contracts, and that's pretty much it. So yeah, that's all we have for today. We have some papers which you already wrote on this, more to come, obviously, and including my thesis. So yeah, if you have any questions, I guess we don't have time right now, but I believe you do have access to our emails, which is actually here. So yeah, feel free to reach out if you have any interest, if you might want us to help you with your use case. So that is all for today. Thank you so much for the attention. Hopefully you found this useful. So yeah, that's all. Thank you.
Thank you everybody for joining us for our last tech tutorial. We will be seeing you tomorrow at the conference. Hopefully, I wish you a nice day. Take some rest and get ready for our first live day tomorrow. And thank you very much, Tomislav and Bogdan, for your presentation. Hopefully, everybody learned something new. Wish you a pleasant day as well, and we will see each other tomorrow. Bye.